In this section, we're going to cover uniform circular motion. Uniform circular motion just means an object that is traveling in a circle at constant speed. The uniform part has to do with the constant speed, and the circular motion part has to do with, obviously, traveling in a circle. As discussed in the unit on vectors, an object that is traveling in a circle is accelerating all the time. And that's because the direction of its velocity is constantly changing, even if its speed is not changing. We'll see that in just a second. A couple facts about this type of motion. If it's traveling at a constant speed, the velocity is always tangent to the circle. The acceleration is always towards the center of the circle. So let's draw a picture of this to illustrate what's going on. Here's my circle, and in green I'll draw my object that's traveling along this circle. Here's a few extra spots to represent where it's going to be in the future. I'll draw my velocity vectors now, and as you can see, I draw them tangent to the circle for each spot. So at the top, that means the velocity is to the side, and then approximately 45 degrees south of west, and then the velocity straight down, and so on, and so on. The acceleration always points towards the center of the circle, so at the top, it points right towards the middle, and then at the next point, and then at the next point. The fact that the acceleration always points towards the center of the circle is significant, and in fact we'll see that any type of acceleration that always points towards the center of a circle gets a special name. That name is centripetal acceleration, an acceleration that is always pointed towards the center of a circle. In fact, the word itself means a center-seeking acceleration. This will have the symbol a sub c. So let's look at the formula. The nice thing is that once we know an acceleration is centripetal, then we have a nice formula for it. And that formula is in terms of both the speed and of the radius. Now, it's not always convenient to measure the speed of an object. In fact, sometimes it's more convenient to measure the period. This is the time it takes to complete one revolution, the time it takes for the object to go all the way around the circle once. The symbol for period is capital T, and the units are in seconds. So now we can use the period to get another formula for centripetal acceleration. To begin with, let's look at the period formula. In this case, the period is 2 pi r over v, where again r is the radius of the circle, and v is the speed at which it's traveling. Because the speed is constant, what this formula really becomes is the distance it travels over the rate. And in this case, 2 pi r simply represents the circumference of the circle, and obviously v is its speed. So I think this formula makes sense. Then we can find the centripetal acceleration using the period by simply solving for v, which is 2 pi r over t, and plugging it into our previous formula, v squared over r. When we do so, you see the result here. A sub c is equal to 4 pi squared r over t squared. We'll see centripetal acceleration in many chapters later, but let's just do a simple problem now just to make sure we understand these formulas. In this example, we have Karen running on a circular track. To find her acceleration, we just take the information given to us and plug it into v squared over r. In this case, we just plug those numbers in, simplify, and get 2.6 meters per second squared, where that's the magnitude of her acceleration, and we know the direction of it is always towards the center of the track. What is her period? Well, again, we just use the period formula, t equals 2 pi r over v, plug in the information, and find that at this speed, she can travel the course of the track in 19.6 seconds.